The second part is about supervised approaches. So we had before methods that based on the data finds a segmentation. Now the next part is where you provide some information to let the segmentation know what it should do. And we have here some an overview of different methods where we can do how we can work this with different with a pipeline. It's a programming concept for actually reducing your programming efforts actually, and then going into classification, regression, and segmentation. This is going really much into machine learning, and there is an ETH course on that one. And another thing we are going to look at very shortly is the UNet, which is a deep learning method for doing segmentation. This gives us a big bunch of modules that we need to use, and they take a little while to load. And what we have basically is in these different supervised methods, we are talking about classification, regression, or a combination of them. And typically what we have is a training phase and a prediction phase. In a training phase, you provide the method with data of what you have measured and what you expect to see. And with that, you build up a model, which is then used for other data where you don't have the ground truth. And that one uses then unseen new data. The classification, we come back again to this blob data, but this time I already have different groups assigned to them. In the k-means case, we did we got just a blank group ID. We didn't know it before, but now we actually need to know what the group is. Again, we get the coordinates and we get the groups. And a classic algorithm, which I actually already touched in the data lecture, is the k-nearest neighbors. And it's very simple method, and I took it up here now with a little example. We have 3 hikers, and one is green, red, and blue, and depending on what they are looking at, they want to determine what kind of forest they are walking in. And the k nearest neighbors actually looks at the closest tree and tells, okay, it's a spruce forest. The next one, he looks at one of the trees, let's say that's one, and he says also, well, this is a spruce forest. This one looks at the trees and see, I'm in a birch forest. So these are the conclusions if they only look at one single tree to say which kind of forest they have. Now, if we would say, let's look at 3 different trees that you can see. This one still says I'm in a spruce forest. This one has a mixed forest, or he would say, if we go for the majority, he would say, okay, I have 2 birches, I have 1 spruce. Okay, I'm in a birch forest or in a mixed forest. And the last one, he only sees birches and he said, okay, I'm in a birch forest. So this is the principle of the k nearest neighbors that you now can change into an algorithm looking at the data. We have, again, the blobs. If we have a point A, it's not really sure what he would say he is. I would say if you only have 1 neighbor, it would probably be the yellow class. If you have 2 neighbors, actually 3 neighbors, then you would say, okay, he belongs to the green one. The plus, the pink plus here, no doubt, he is certainly in the green area. But the orange dot here, he also has to decide how many neighbors he needs to check. And if you only look at a single neighbor, he would say, I'm green. If he looks at 3 neighbors, he would say, I'm, what is it? Some dark purple color. That would be a different class then. So it depends on how many neighbors you consider in order to make your decision. And looking at a text example where we have a vector containing values and words. And if you give a value 1, then it corresponds to I. If 2, am, 3, a, and 4, a dog. Dog. If you look at a k-neighbors classifier with 1 neighbor and try to put in numbers in that one. Let's go out and look at that. Now let's predict based on a vector with the numbers 0, 1, 2, 3. And the output will then be that it predicts, okay, I'm a dog. If you now would put some other values, not the ones that it's actually trained for, like here, I would take 1.5, which would actually be in between 1 and 2. Then it would say 1.5 corresponds to am. If you put 100, which is way beyond the 3 that we had trained with, it takes still the dog because the dog is closest to 100. Oops. Now, when we go back to the blob data, we can also try to do some work here. We have our groups in the training. And now we want to see what we can do with it. We train it with this data. And we only have 1 neighbor. And now we actually create an array with testing points. So we have different coordinates and then we probe each one of these coordinates. And what k-means gives us is then pretty curved decision lines. And in here, you can even see that there is interleaved points from the different classes. And this may be good or bad, depending on what you're looking for, but this kind of uncertainty in this region is usually not good for your decisions. So we want to make it more robust. And with that, we can do a k-neighbors classifier with 4 classes instead, 4 neighbors, sorry. And now you get nicer decision lines, and they mainly make sense. This one will be misclassified because it's too far away from its home. But now we have nice, more or less nice lines in the data. Linear regression is something that you probably have used a lot already. It's just linear curve fitting. And it tries to fit a line through points that is given. And sometimes it can even be points in more than 1 dimension. It's easy to understand and interpret, and it's also relatively fast to compute. So let's take the basic data set. We have 2 arrays with the numbers 0, 1, 2, 3, and that corresponds to values 10, 20, 30, and 40. We get this straight line doing a fit to it, and we see that the slope is 10 and the intercept is 10. So that's not very special about that, but now we want to bring that into our data and see what happens. And let's create first some data points based on this model that we already made. If you put in the values that you trained with, of course, you get those values. If you try with a -100, you get -990, 500, then you get 5010. So this is just a straight linear equation. So it's nothing particular about that. Now, if we look at regression with the blob data, now we have X and Y coordinates on one side, and they are associated with two classes, 1 and 0. So the data in this case looks like this. We have one dominant part up here and one dominant part down here. And then we want to find some kind of regression for that. And the model tells us we have different slopes, we have an offset. Okay, that doesn't tell us so much yet. But now if we look into it and try running with the test points, we can see that we have a continuous gradient here. So if you have these test points with the coordinates, they will give something that actually has a tilted slope here, a tilted gradient. And the values we don't see right now, but we had in our data ones and zeros. So what I did in this test image is that I apply a threshold on that data at 0.5, which is just in the middle between 1 and 0. And that gives us the segmentation that all data in this part here belongs to one class and all data belongs to the other class. And that actually matched pretty well with the test data. So the regression was able to separate between the two of them. Another thing, another way to do very nonlinear segmentation is to use decision trees. And a tree structure is something that is very common in computer science, where you do separate your data, you categorize your data based on some different criteria. And see if my pen is working. Yeah, it's working again, yay. So what is typically happening is that you have trees, binary trees, which, oops, no, something crazy happened. Hey, come on, let me loose. Yeah, I think I start on from the beginning. So you get trees like this, where you can split down, and it's based on different criteria. You go down in this tree and you have pretty quick searches in it. So typically if in a binary tree, you have the search depth that you're looking for is usually logarithm of the second logarithm of the number of points you have if you have a balanced tree. And the task of decision tree learning is that you have to create a tree which makes it easy to take a data point and let it bounce around in the tree and give you the answer what it is. Now we do a fitting of a very simple use case, which, oops. Let's see, that one didn't appear. That was not good. Why not? Oh, okay, I need to run it all the way because I want to show this tree. Ah, there we have a tree. Good. Let's go back to that one. So there we have our tree. So what we have here now is a data vector with input data. We have 0, 1, 2, 3, which is associated with 0, 1, 0, 1. And when you look at the data vector here now, you see that if it is less than a half, then it should go here. And you have one sample, so less than a half gives you a 0, and then you go here. All the other data points, they are split up now, and we have a new selection criteria here, 1.5. So that would be between those two. That would give us a 1. and go on. If it wasn't true, then you go here and set a new threshold. It's 2.5. That would be between those two. Then you have either a 0 or a 1. So the output values are standing here. No, this one doesn't have an output value. Here you have a 1, here I have a 0, and here I have a 1. And when you have these values, then you would be able to fit to get an answer pretty quick. This particular tree is rather unbalanced because you always have everything going along one search line, which is very inefficient. So mostly the tree fitting models, they try to balance a tree so that it's equally heavy on both sides. Looking at trees in the blob data, we again have the same blobs, the three blobs. And we try to train our tree on that. And this one doesn't work. Oh, again, it's not activated. Seems I need to run through a couple of things. Yeah, here we got it. Just do all the other ones too, so to be sure. Sorry for this interruption. And I go back to that one. No, that one. So we have our blob data with 3 classes. We train it, and now we get a new tree. We only have 3 classes, so it's relatively simple. But anyway, we have here now a splitting on some value. Now you can see that you split again only on one value. And what the result is when we try to run the decision map, look at what the decision map looks like. We have testing points which run over the data, and it actually separates the data in 3 blocks like this. It kind of makes sense actually, but it's not a good segmentation because many of the data points over here, they would probably rather be in that one. So you can think of maybe better segmentations. To get rid of this problem, we have something called random forests, and that's a one simple way of handling it is that you split your data in several segments and you train different trees on each segment. When you want to predict something, you let the data and your test point into all trees, and then you see what is the decision from each tree, and then you take the majority answers, gives you the class. There are also other methods to do this, but majority voting is a pretty basic one to handle. And now we make a little bit uglier data set. So the standard deviation in this data set is much wider. And you can see that there is a great overlap between them. And with this data set, I want to try a forest with 5 different trees and see what happens. So we have built our tree. And now if you want to look at it, it is a very big thing. It's a very complicated tree. I'm not going to look into the details, but this tree is huge, and this is only one of them. So we can actually look at another tree, which is even larger. It's also again, oops, sorry, now I got lost again. So you have very many different tree structures, and each of these trees, they should produce a result together. And looking at the output of that, we have our training data, which is very overlapping, and the decision of the random forest classifier looks like this. Of course, it has some overlaps here, uncertainties, but on the other hand, we have to live with it, because, or we have to train the tree differently, setting different criteria, saying we want more trees is one way of handling it. And you can see here that the first tree is pretty crazy. This one is wild, even finding something here with a breakup. The advantage of trees is that you can really find a very detailed regions within your classes. So it's a very nonlinear classifier, which can be very useful in some cases. But you have to select the task for the tree classifier to get the right values, to get the right results. Now we're going over to a technical component, which is called a pipeline. And usually when you do processing of images, you have a very clear chain of operations. So first you do some kind of normalization, then you may do enhancement, then you do some segmentation, then you do analysis, and so on. And you can see here that it's a linear sequence. One is done after the other in a clear line. And this is what pipelines are for, to support you, so you don't have to write that code, and you can actually configure it relatively flexibly if you want to do larger data sets, larger processing of your data. So let's create the blobs again. We know them pretty well by now. And now we create a very basic pipeline, which consists of a normalization. So it does only a robust scalar. It normalizes the data with this average value and standard deviation. And this is what we get. Then you can see the histograms of the data, that here it's pretty widespread, and here it's now centered around 0. So this was our very basic pipeline. You only give it a list of commands, and that's it. So next step, we maybe transform it a little bit in some quantiles, and then into 2 quantiles. Then we do the rescaling, and then you get some data out from that. These are basic pre-processing operations. And now if we want to add some features, could be that we want to create more features in our data set. And in this case, we want to create polynomial features, meaning that we have first order polynomial, second order polynomial. In this case, we go up to a polynomials of second order, which means that we have 3 data sets coming in here. And we create now 10 different, because we have the original, and then we have the different polynomials of each of these components. So you can see that the data is growing now, but you didn't have to do much of coding except just saying you want to have this and that. This would have been a little bit more work to handle. And then we can use these pipelines to do our processing. We start out looking at numbers, and the MNIST data again, handwritten, but you can also segment anything you want to put into a category. Let's load the MNIST images. We got 50 images, size 8 by 8 pixels. And let's put them into a pipeline. The first step is we have the input data like this. So we see a lot of numbers. Each number is now created as a flat vector. Because these classification methods, they don't like images really, many of them. So we just want to fix them into long lines instead. Next is to normalize the data. And then you can see here what the histograms are looking like after these steps. We haven't done any segmentation yet at all. or classification. So now let's add a classifier. So let's create a k-neighbors classifier with one neighbor. And then it creates something like that here. It's just what the output is. It's a bit hard to interpret what it actually means, but it has at least some information here. So let's try the performance of this classifier. So now we use this pipeline to predict based on some image data and see what happens. Now, we put in the training data as we had it, and we can see that, well, great. This one actually produced very good confusion matrix. All numbers are where they should, and that's good. We can maybe think, but not really. So let's look at this. We have very good support. We have nice precision and recall in this, but something doesn't fit really. We shouldn't be that good. And the problem is that this algorithm didn't see any any new data. So let's try to create some kind of digit. So I just blob in some pixels in this, and we expect this to be a 9. But what the pipeline predicts is that it's a 7. So we're not really that good. And now we come out to the idea when you do use these supervised methods, you always have to have a training set, validation set, which tests the performance. And then finally, you have to have something that tests and really clears out that you have done the right thing. And that is what you need to really set up when you do this training. Meaning for the numbers, you should probably do something like, I don't know, 30 images for the training and 10 for the validation and 10 for the test. That would be a nice split in this case. So we did something really bad because we would actually mislead our evaluation by using the same data for both training and testing. We can also do regression using the pipeline and see what comes out. Now we get actually numbers instead of classes out of this tool. And again, we have the flatten normalization, and then we have a nearest neighbor regressor. And that one should give us some numbers out. And it looks like pretty good. We have here, you can see that's really a sequence of numbers. So it goes from 0 to 9, 0 to 9, and so on. So you can see here that the input, expected input, also produces something that looks like what we would expect. Only down here, it's a bit mixed up, and I think that also goes pretty well. So, but now we tested it on the true, on the input data again. But it's harder to see. So we would need to actually do a nice split in the training and test data. Now, if you have multi-category data, so you're not only having a single number, but or true or false, or black or white, or whatever, then it's harder to see how we can assess the results. So we can't use the ROC curve, we can't use precision and recall. So we have to have something else. And we actually already looked at some metrics, mean squared error and mean absolute error are two numbers that we can look at. And then we can look at predictions with the data. I think we got some more. Let's see here, what is it? Yeah, so let's go in here. We have the regression pipeline again. We do prediction on the image data. And now we plot the full data set, I think. and see here how well it does. So we have predictions on the training data. You can see that's pretty good. There are some misses actually, but mostly the regression does the right thing. Now, if we do the same thing on the validation data, you can see that there is a big spread on many of them, meaning this regression model was maybe not as good as you would like it to be. So for example, the 2 is very hard and it's actually misclassified as probably a 5, which is strange. So this is what we get when we use the true test. So what we can do is to increase the neighbors and see what happens. And here we have the k-neighbors regressor with 2 neighbors instead. And you can see that starts being a bit jumpy, even with the test data. But anyway, this is what it looks like. And oh, that one didn't show up. And I need to actually. And here you can see also here, it was maybe not so good still, but you get at least a bit better on the ones. No, it's the same. Yeah. So this would be a way to handle it, to increase the numbers of neighbors. So let's go back to, let's see, what time is it? 55. Oh, okay. I'm actually running out of time. Do you mind if I do some overtime today? I think I need until quarter or maybe 20 past. Is that okay? So someone thinks it's good. So let's go on. Let's go on to segmentation. Now we have only done some classification, the whole picture classification or whole image classification. Now we want to look into single pixels, what they are. And this is also a problem that we want to solve in a good way. And the mitochondria was a tricky one. We have already seen it. It's not easy to find the right stuff. The signal to noise ratio not ideal. We have almost the same signal to noise, same structures and same gray levels. But human eye can easily spot them. So that means there must be a way to handle it. So we can try now. We already tried with thresholds and we tried with filtering, but it didn't really help. So we can try that now using decision trees, random forest, linear regression, also doing nearest neighbor, and we can see what that comes. And this one, I actually have to switch now to the notebook because this is something that takes a little bit more space. But let's look at the image mask. We have here the image and we have the mask, what we would expect. So let's run the pipeline. First we create a training image and then we have a validation image. So we actually split the image into 2 pieces and see what comes. And let's see, first step is to go to the regression tree. We see that it does some training and let's see what it comes out. The regression tree didn't produce anything really useful actually. You can see here in the prediction mask that there is still a lot of pixels. So there is a high probability that you have objects everywhere, more or less. So you get all structures, which is not what you want. Then we can try adding regression tree with position information. Then we have the image and the positions here, which is flattened, and then you get something looking like this. This gives gives a little bit better result. You can see here that now you get at least some kind of blobs on the right places, but these blobs are not very good. And looking at the full image, we see that in the trained part, we get the blobs more or less what we would expect them, but out in the unseen data, we only get things that touch the blobs. And then it's more or less the original image. So also that didn't really do so well. Then we can go on adding more and more. We can do random forests and see what they do. But actually, random forest did improve. So you can see here now that the random forest actually got the blobs, all these nodes, on the right places and with pretty good confidence. But if we look at the full mask, then we are in unknown territory and it starts inventing stuff, even worse than the other ones. So also this one didn't really work that well. Then we can add on polynomial features, see what happens if we do different polynomials on the data. And the prediction mask is still good. And this was still a forest, but the forest couldn't do any good work here either. So then we can try doing different filtering, like doing Gaussian, doing difference of Gaussians, a wider difference of Gaussian, see what happens. We get weirder and weirder data vectors. The prediction mask usually do good on the training data, but we never reach out into the real data. Next thing would be to look at neighbors. So looking in the pixel neighborhood of each pixel. And that is done by kind of jittering the image a little bit. And then we create actually 9 replicates of the original image with pixel shifts in ±1 in each direction. And see what come out. We do a regression of that. It predicts, not really a good thing. You can see again, we get all the structures are likely to be, and it goes on with the same thing here. But the interesting thing is, what we did now was actually, when we created this image, is actually to look at a pixel neighborhood, and that corresponds to a filter kernel, more or less, with the values like this. So we could actually do this same pixel shift operation. We could do that as a convolution, but this pixel shift, the regression gave us the filter coefficients that we need to use, which is actually a good thing, because then now we have something that fits to the data, even though it doesn't really give what would help us much. But anyway, it can give the same result as with convolution as when you did a linear model. So we can also look further on using nearest neighbor regressor, see what happened then. This one is just, this one is also doing the neighbor stepping and see what happens. So the nearest neighbor regressor again does a better fit on the training data, but on the prediction data, on the validation data, it still has problems. So to go back to the slides again, this was a very quick overview of how you can combine different ways in pipelines. And the programming effort is usually just that you add an element within the pipeline list. So it's a very easy way to go on to defining these things and test them and evaluate. It can help to generate features out of the data, but it's, in this particular case, it wasn't really a good one. We usually failed on the validation data, and sometimes we failed on both validation and training data, which is not a very good segmentation model. So we seems to need a new way of handling this segmentation task. And what comes to our help is deep learning methods and machine learning technique, neural networks, is very popular to do this, and one that has gained a lot of success in for image processing and segmentation in particular is a model called UNet. And the reason is that you can kind of draw the network as a U. And what is happening with this in this network is that you have some convolutional layers here. So in this network, you're creating nodes with help of different filter kernels. And these filters are applied, and then you create weights and you're propagating the information through this network. Now I don't have the time to fully explain everything about neural networks, but the principle is that you're working on different scales. So you do some processing on the full image size, then you do downscaling, do some processing here, downscaling again, some processing, downscaling. And then once you are on the lowest level, you go back again, up. And you also use information from the same level. So the gray arrows here, they produce, send information from the same level over. So it's always combining downsample data with same size data. So it's a very big and massive model. And you can, with the help of TensorFlow and Keras, you can define it with very few steps. You can see here. This code actually produces a unit that is supposed to do a segmentation for us. And that's not much, maybe a bit to digest, but comparing to everything that is happening here, you have a lot of convolutions, you have a lot of matrix multiplications, you have downsamplings, upsamplings, etc. This is actually handled within these about 30 lines of code. So it's a very compact way of writing. So doing using a unit is not that much of code writing, at least not to begin with. And then you can get a summary of the network, which tells us a bit about input nodes and how they are connected. And then we can start again. We need new training data. Neural networks is something that is very computationally intense. So for this case, I'm downsizing the data to speed up things. We again have a training image, a validation image, and let's see what we get out. We have just now built this model. We didn't train it at all, and we can see what comes out. What you get is here you have the full image, and this is what this network is predicting. So it essentially looks like something that the regression models could do. Not so fantastic. And let's see what happens after we do the training. But before that, I just want to give a little note on this demo. And that is, usually when you do training of neural networks, you use a lot of data. You should use very well-defined data sets for training and validation, and also for the testing. I'm not doing it here because I only have one image. This is bad work actually, but now for this demonstration, it shows the concept at least. So we need to have some kind of training conditions. We need some loss function, which is the optimization of this training needs some value to be guided by. Here we have the mean absolute error, and we have an optimizer called stochastic gradient descent. We train 20 epochs, which mean 20 iterations of this training, and then we see what comes out. And then for the validation, we have metrics like binary accuracy, and also the mean absolute error. There are also a catalog of very many other metrics to look at. Another one is dice score, which is looking into true positives and false, so true and false predictions in the data. So let's train and see what happens. This one, I think I need to run actually. So this takes a little while to run. Now I switched off the verbose, which is maybe stupid, but no, oh, I didn't execute that one. Sorry. Yeah, we can look at the curves anyway. Yeah, we can. So I didn't execute the cells above. Anyway, from the training, we can see that we have training and validation data for the mean absolute error and the classification accuracy. And you can see that the error is lower for the validation data than for the training data, which is maybe a bit strange. And then we have the classification accuracy. They must have been switched. That doesn't make sense. But anyway, we can see here that we reach up to about 91, 92% accuracy in both training and validation data. So let's look at the images that we get. This wasn't so very nice. So the reason is, I would say, is, let's see here, I need to change a little bit. No, the reason is the grade level scaling. Sorry for that. I forgot to update that one. Actually, I should go back and do it. So let's do the whole process and see what comes out. No, I'm not there. I'm not there. So let's execute the cells. So this is what the network looks like. It's a different way of illustrating it. And we have those and training data and results of untrained method. And that you got that. Let's train it. Oh, now this one probably takes about a minute to train. On this computer. I'm not using graphic cards, which is very popular because that speeds up the processing a lot. And also in machine learning, it's very common to use cloud computing clusters because sometimes you can have trainings going up to several days until you see the output. So there we got it. And there we got that, and we can see. So now we got a nice one. So good. So what you get now is probability map. It's not really the segmented images, but the probability that it is matching the features you want to look at. And afterwards, you have to do a simple thresholding of this probability map. There you can still see, until now, this is the best result we have seen in any of the other approaches. This was using a very simple unit. Actually, now, to be honest, on bad training data. But anyway, it's producing something that looks very reasonable. A problem is we have very, very many parameters to optimize in this. Each layer contains a lot of convolution kernels. We have weights between all the levels in the network. So that one is needs to be fitted. And a problem is we can get very good data on the training data, but it can be very specific and it hasn't been generalized into other kinds of problems. So if we would possibly use it on a different image with maybe a little bit different light conditions, we wouldn't be able to do any good at all, because this is very nicely fitted to exactly this problem. And that is something you have to look out for when you do training of deep learning networks. So you have to be you have to provide a lot of training data with great variations within it. Otherwise, it's not going to be good. Then we have another one to execute. Oh, it's again, let's train again. It's just a short one. And run on. And then you can see again, you have some different errors and classification goes down even. So it's not a good case. You can see that this model is actually misbehaving and doing the wrong thing particularly in the accuracy of training and validation. Well, not so bad actually, 89%. So it's still in a decent level, but you can push these methods should actually be able to push you up towards the 99% precision. Let's look at this one again, see what comes out. That one didn't come out nice, and there come a warning too. Okay, yeah, well, that was a little demonstration of what you can do with deep learning. Important thing is with this supervised methods is that you have good training and validation data, and you really make sure that you have split it up into training, validation, and testing. Otherwise, you may do wrong modeling of your models. You have a lot of different methods to work with. The deep learning is, as I say, the heavy gun, but you can use simpler things like trees and nearest neighbor methods. So you can actually, you have to work with a specific palette of tools and select which one actually makes sense best for you, because the more complicated model you use, the more time you have to spend on making sure that it works. But well, then we come back to Occam's razor. The simplest method is usually the best, as long as it works. So start simple and see if you can handle it from there, or you have to go to more and more complicated cases. And that was all for today. And now we have a little bit shorter time for the exercises. I have to run away now. I have a seminar to attend to, but Stefano will take care of you. So have a good week.